Module 5 contains two modules associated with computing natural frequencies and mode shapes. Module 5A will cover linear systems, while Module 5B will cover systems with load stiffening. The model used in the analysis is the same cantilevered beam used in Module 4. The details of this model and how it was meshed are presented in Module 4A. We will demonstrate how to set up a natural frequency analysis in Autodesk Simulation Multiphysics by editing the analysis parameters. This is done by selecting Analysis Type, right-click, Edit Analysis Parameters. First, we must specify the number of frequencies to be computed and the frequency range where we expect these frequencies to be found. The number of frequencies to be calculated depends on their intended use. Since we use the natural frequencies and mode shapes to compute a transient response using the modal superposition method, we must consider the nature of the load that will be applied. The load to be applied in Module 6 will excite primarily the weak axis bending modes. Preliminary analyses have shown that accurate results can be obtained in the transient analysis if the first three weak axis bending modes are included. Preliminary analyses have also shown that the first three weak axis bending modes are contained within the first 5 computed modes. Therefore, the number of computed natural frequencies and mode shapes will be equal to the default value of 5. The first 5 modes fall within a frequency range of 0 to 1000 Hz. Therefore, the lower cutoff frequency will be 0, and the upper cutoff frequency will be 1000 Hz. It is often necessary to perform multiple analyses to determine if the desired number of frequencies and types of modes are contained within the frequency range specified. At this point, we are ready to submit the analyses. In Autodesk Simulation Multiphysics, we select the Analysis tab and then select the Run Simulation icon. The analysis has just completed. The natural frequency associated with the mode shape displayed is shown in the lower left-hand corner of the graphics window. In this case, we are looking at Mode 1 of the 5 computed. Mode 1 has a natural frequency of 28 Hz. The scale factor used to display the mode shape can be increased to improve our ability to visualize the mode shape. We will increase the scale factor to 15% of the overall model size by first selecting Show Displaced, followed by Displaced Options. The scale factor can be set at 15 and the options menu closed. Examination of the first mode shows that it is the first weak axis bending mode. Each mode is treated like a load case, and we can select the mode to be displayed using the load case arrows. Mode 2 is the second weak axis bending mode that has a frequency of 175.7 Hz. Mode 3 is the first stiff axis bending mode, and it has a frequency of 222 Hz. Mode 4 is the third weak axis bending mode, and it has a frequency of 492 Hz. And finally, Mode 5 is the first torsional mode, which has a frequency of 616 Hz. This completes the video.